My name is Gabe Prado. I'm a product marketing manager at SparkCognition. I was here last year giving a higher level overview of AI, some of the terminology, some of the principles around what makes AI, some of the terms that you start to hear. And over this past year or so, I've been to a lot of different conferences where there's a lot of AI messages that are still at a very high level. So what I'm trying to do with the presentation today is bring some reality into this, show what's active, show what the requirements are, show some of the best practices around what you need to be looking for in your AI applications. But I'll give a quick introduction around SparkCognition. So we've been a company since 2013. We're based out of Austin, Texas. We've been in the AI space for about 5 years. And we're one of the world's leading AI platform companies. Now what that means is that we're commercializing AI technology, cutting edge AI technology, and commercializing into repeatable, consistent products that we sell for different domains. So we work very closely with the University of Texas to look at groundbreaking research and turn that into products. Our mission statement is really around trying to advance the most important interests of society. So if you think about energy and all the pains and challenges in just producing the energy that we use on a day-to-day basis, we help make that cleaner, more efficient, and more productive. Similar for transportation, right? Transportation, we're actually working with Boeing on the transportation systems of the future so that people can get from point A to point B safer and more effectively. And how do we even start to bridge this gap between all the physical transportations happening now and all the automated transportation that will happen in the future? So there's some exciting stuff there. And then you think about government defense as well, right? The implications for our own security. There's a lot of AI applications in that domain as well that we play in. Like I mentioned, we commercialize AI research into 4 main products. 2 of them you consider to be platforms, 2 of them more solutions-based. Our platform, Darwin, for instance, helps automate a lot of the complicated parts of the data science process. So if you think about a data scientist who has too many projects on their hands that needs to prototype and experiment and iterate rapidly, this is a really good platform for them to use to help make their job easier. DeepNLP is another type of platform that essentially takes unstructured data, so language data that you find in a book or in a PDF or an email, and turns it in and makes it structured, turns it into a tabular format that you can use to derive insights and context. And then we move to our products. So Spark Predict is one that I'll probably spend a little bit more time talking about the technology around it because it's a little bit more IoT based at the moment. The Spark Predict is our predictive maintenance solution for complicated and critical assets. And then Deep Armor is our cybersecurity product that uses machine learning to make predictions on malware threats rather than actually using any signatures or heuristics. So if we bring that back, again, as a leading AI platform company, the applications for AI are across multiple domains. And we can actually weave these different products and platforms together to create really compelling solutions for a customer. Now, if you kind of look at the timeline, back in 2017, our technology was proven and was very much disruptive, right? And we were recognized by the CNBC Disruptor 50 list right next to Uber. And so it speaks to the power that AI will have on the application in the future. In 2018, we were consistent in this, right? We were Wall Street Journal's top 25 tech company. So the technology continues to grow and incubate. And then most recently, I think something that we're very proud of, in 2019, we were for the 3rd year running on the CB Insights AI 100 list. And what we're most proud of is the fact that we're ranked number 9 in terms of AI patents. So again, going back to that story of we're commercializing cutting-edge research into products. Now, I think it's important to take a look at the fundamental concepts that make all of this work. These are, again, cross-domain, but these are the foundational principles that make our technology work and are used to actually drive value. So if you look at reinforcement learning, this is the concept around, if you give a machine a desired output or desired problem to solve, and you give a series of weighted awards or rewards and penalties, how does that machine actually figure out how to accomplish that problem? So if any of y'all have ever learned how to walk, it's a similar principle, right? It's how do you learn how to actually make that process work? By failing sometimes, by putting that first foot in front of the other one. It's a really important concept for a lot of what we're doing with AI. You also look at genetic algorithms. These are algorithms that pass the best characteristics of the model or the algorithm on to future generations of algorithm. So we're learning from the first models, we're learning from the first generations and passing the best stuff forward. We move into automated model building. And this is another really compelling area because I think one of the problems that a lot of people are trying to solve is in scale. How do you automate some of the complexity in building models? This is a core piece of some of our IP. Transfer learning. This is, I think, one of the most exciting pieces of research at the moment. And this is the ability to generalize behavior insights from data across other similar types of assets without needing that same data stream. So if you think about a brand new asset or brand new machine that you don't have any historical data for, you can generalize some insights from similar machines and use that to build a model. This is hard to do, but this is what's going to enable that scale in the future. And then kind of at the core of it all, it's about deriving insights from every piece of the model, every piece of the algorithm. We're trying to make things as explainable as possible so that not only can you understand the output, but you can understand the decision-making process and the evidence for why that machine learning model came to the conclusion that it did. Yeah?
So you've got a picture of a neural network there on automated model building or something like it. That's usually not in the realm of what you would call explainable AI. It's usually very opaque. Are you building neural networks that humans can actually understand the innards of, or are these different sorts of algorithms, or?
Yeah, so the neural networks that we're building, we are providing one will provide the output of the architecture for our, in some cases like for Garden, we'll provide the output of the architecture. In other cases, we will actually provide all the contributing features and the level of priority that created the output that you see. So at a quick level, you can understand the output and then what are the main drivers of that output.
Okay.
Yeah, but we can talk more.
Yeah.
Still.
It's got to be. I mean, a deep convolutional network has just got too much going on. It's very hard for a human to.
Yeah.
Just a quick question. Are you guys doing the general adversarial networks as well?
I am not as familiar with that domain.
Two AIs fighting each other?
Not that I'm privy to. But yeah, so I think one of the stories that that's very relevant for you guys is all of you guys are probably involved in some way, shape, or form in digital transformation, right? This is the main one of the main value adds of the IoT space. And a lot of companies have spent a lot of time, a lot of money, a lot of effort into digitizing everything so that they can make use of the data. But making use of that data is still very hard to do. Like Bill mentioned, right? How do you actually leverage this data to drive actual insights and make decisions based on that? And it comes down to a lot of customers having issues with the capabilities, right? They may not have the internal capabilities to handle that. They may not have the tools or the strategy in place to actually make the data usable or even curate the data in a way that it can be usable. Now, AI doesn't solve all these problems, but AI can actually help with a structured data set, or with enough structure around data, can actually make this valuable over the long term. And so we're helping to deliver more value from all the efforts that have gone in to digital transformation and delivering value over time. So that's a quick peek at what we do. I do want to spend a little bit of time on machine learning, but any other questions so far? Yeah.
So if I have a swarm of drones, would you interface at the swarm level, or how would your technology kind of interoperate between a swarm of drones?
That's a good question. So it's going to depend on where the control system lays. So if you're communicating drone to drone, I'm probably not the most authorized person to talk on
I
this.
understand, yeah.
But maybe we take that one offline and I'll find you after the presentation.
Does your stuff run on device in general, or is it generally just on the back end?
In some cases, we can deploy on device, on-prem. Other cases, we deploy through the cloud.
So are you guys
different
working-
implement options.
You're using the accelerators? I mean, a lot of chip companies are starting to build AI accelerators, tensor processors, cameras with AI built into them directly. Are you guys looking at all the variations of hardware, or?
Yeah, we've got partners like HP Edgeline where we work with AI on the edge, and it really depends. Now we consume that, we consume data, and then we work with the vendor, work with the device to actually figure out what needs to be processed on the device and what we can do remotely.
Okay.
So it's, again, the application of that is varied. So if we break down, just to kind of level set everyone, if we break down AI and machine learning and foundational concepts, AI is kind of that umbrella term for a lot of things. So this is what is creating a lot of noise in the market, right? Everyone's talking about AI in some way, shape, or form. So I'm going to try to dig into that a little bit and unpack that. On one hand, you have artificial generalized intelligence, and this is some of the Skynet stuff, right? This is the means for a machine to generalize information and be able to make decisions across multiple domains, right? They can draw correlations, they can understand stuff across a multitude of information. We're not there yet. Where we are and where we're making quick advances is in the field of expert systems. Expert systems is where you have a system that lives inside a particular domain and given a specific data set can solve problems to a very high degree of accuracy. Now, this is where we break it down into machine learning versus natural language processing. As I mentioned earlier, natural language processing is the ability for a model to interpret written data as it were a human. So it understands the context, it understands a lot of the nuance, and it can pick apart insights given a unstructured data set. So think about all the emails, think about all the maintenance logs, think about legal documents. There's a ton of unstructured information that we can tabularize and actually make very useful. Where I'm going to spend most of the time talking today is really around machine learning. And this is where you hear about models and algorithms. These are the foundational blocks that make machine learning work. This is how machine learning can learn from a data set and continue to learn against new data over time. And then we have the neural network architecture as well, where we're starting to put together some of the processing and mimic some of how a human might solve a problem by using sophisticated neural networks. And usually under here you hear terms unsupervised, supervised, reinforcement learning. I kind of covered reinforcement learning earlier. But unsupervised learning is the means to give a model a data set, an unlabeled data set, and have that model figure out all the patterns that are important. And then be able to, with some coaching, with some human intervention, actually be able to figure out what those patterns mean and actually guide the output of the model. Supervised learning is a little bit more structured, where you give a set of known inputs and a set of known outputs, and the model figures out how to repeat the process for getting those outputs over time. This is supervised learning, something that I think you see a lot of, right? So if you, last time you've been on Facebook, Facebook is recommending what to put in your feed based on what all your past behavior. They know what you're looking for, and they re-engineer that back to provide content that's similar to what you're looking for. I saw a question over there.
If you could go back to the previous slide, I would argue that it is possible to train natural language models as part of NLP as well. So in some sense, natural language processing does involve machine learning. So,
Sure, absolutely.
I mean, previously you used to have rule-based systems, but those are not scalable. So natural language processing does involve machine learning.
Absolutely. So there's the part of deconstructing the unstructured information and making it tabular and useful. And then on top of that, you can apply models to that tabular data to actually build models that contextualize that information. So great point. Yeah, the point here is that you guys are interacting with machine learning every day in some way, shape, or form. Now, if we move this into the IoT domain, how do we kind of start to conceptualize this and look at this? We break it down into the physical domain versus the digital domain. So we start with sensor data from IoT-equipped assets. So we're looking at, in some cases for predictive maintenance, for instance, we're looking at temperature, pressure, flow, vibration. We're looking at process data that we need to somehow aggregate in some way, shape, or form. This connection here, I think, is one of the bigger challenges that I'll go into in a minute. But being able to translate the data from sensor data to usable format is still very hard to do. So we work with a variety of vendors to actually aggregate and make sense of that data. Now, once data is in a usable format, it's been aggregated, it's been consolidated, and it's been somewhat normalized, we can then use it to build predictive models using a variety of approaches. Now, kind of going back to my point about the SME being in the loop, in some cases, it's really important for that subject matter expert to actually be there to help guide and validate the output of the model. So you're building a really accurate model, but you still have checks and balances that need to happen based on the subject matter expert to actually make sure that that model is usable long term. Any questions so far?
I'd just like to reiterate that because I know in my experience, we've had product managers come and ask us to do machine learning, and they expect to throw all the data against the wall and get magic answers.
Yeah.
And that is a hard deal to fight against. So we always try to say augment. Augment the expert with your tools, and then to build that knowledge, and then your model gets trained. Excuse me.
Yeah, no, that's a great point. There's still a strong handshake to make the outputs usable, because you can have a model spin something out, but if you don't know what it means and if you've got a data scientist who has no domain expert with the actual, or no domain expertise with the actual problem, you're not going to get something valid. Yeah.
On the slide, it shows the consumption of the data. You said it's real time.
Yeah.
Based on the use cases and what your customers are asking for, how real time is that real time?
Sure. Real time can mean a lot of different things, right? You're looking at megahertz or millisecond resolution all the way to minute resolution, right? So there's different ranges. For some use case, and we can work with multiple ranges. Typically, our customers are coming to us with about minute resolution, right? So it's a little bit, but as we get better edge processing, as we move closer to the device itself, we're moving closer and faster.
And as the devices get more powerful.
Yeah, exactly.
Excuse me. So
yeah.
Could you go back to the previous slide? So you were showing a digital domain there. So the tools that you have a favorite cloud solution that you use? Or?
Yeah, so we're partners with Google Cloud Platform. We've done some work with Microsoft Azure. The actual consolidation of the data is not a blocker, right? So if a customer has a data set or has a database that we need to build a connector for, we build a connector for. So that's not necessarily a limiting factor. But I think what you're trying to ask is, do we deploy on cloud or on premise? And that's also flexible. We've done both applications. Does that answer your question?
Yeah.
Okay. So we've done this enough to start to be able to define some of the best practices around data, right? Without good data and without the right governance and the right systems in place, you can't have a good machine learning project. And this is what I think people are starting to learn very quickly. So if we look at kind of 4 pillars that we like to recommend as being things that you absolutely, before starting on a machine learning project, you should be thinking about. It's really around the quantity of data. Do you have enough quantity to make a model, right? The model is, you're going to feed a model enough data, and the more data that you give it, it's going to be a stronger model. So for instance, we recommend about 6 months to 2 years of data as being a safe range. Because if you think about it, about 70% of that data is going to be used for training of the model. You've got about 15% of that data that's going to be used for validation, and then another 15% of testing, all before it goes into deployment. So you need a lot of data for this to actually make sense. The other piece is around the quality, right? If you're looking at IoT sensor data, are the sensors even valid? Are they calibrated? Are they up to date? Is there governance around that? Do we have missing information? Do we have garbage information? How do we gauge the quality of that data before giving it to a model? Because again, garbage in, garbage out. Another thing that we've seen happen a lot over this last year is just how do we get to the data? A lot of times this is governed by IT, or this is located on a server that's actually really hard to get to. So if you haven't figured out, if you know you have data but you haven't figured out how to get that data out, this is a conversation to have with that IT department or that data stewardship group to have it early so that you don't go down, you've established the business requirements, and then you get stalled because you can't get to the data. We've seen this happen more times than you can count. And then this last one, this concept around reproducibility, is really around scale, right? So if you go through the pilot phase of a project with an AI project, but you haven't orchestrated the same or similar data requirements for all your other assets, it's going to be a completely different ballgame, right? Because if you have different instrumentation systems, different data acquisition systems, and your data looks different, you're going to go through a similar process over the course of that, a similar rebuilding process over the course of that actual deployment. So the best practice here is, if you have that opportunity to spec out systems, and if you're starting from stage 1 or stage 2 digital transformation, you have that authority to actually build in the data systems. It's really important to think about reproducibility at the end. How can we make our data acquisition consistent? So we'll move a little bit deeper into a real-world example. But this is for a predictive maintenance application. But what I'm trying to show here is that there's multiple ways to actually solve this problem, right? Sometimes it may seem that there's like a one-size-fits-all, but there's actually multiple scenarios, multiple domains, or multiple ways to actually solve this problem. So we start with an industrial asset or a manufacturing machine, or this could be a power generation turbine, this could be a pump, this could be all sorts of IoT-equipped devices. But we typically find three different failure scenarios. There's a failure that occurs completely randomly. It's completely unexpected, and there's no way to have anticipated or build in a rule to detect that specific failure mode. I'll get to your question in just one second. These typically, occur very rarely and are high risk to the business because, again, you can't plan for that. You can't build a solution for that using rules or using some of the legacy methods. So what do you do? The second scenario that we come across is when there are a variety of failure modes that occur randomly, right? There's typically some history in the data. We know a little bit about how these failure modes develop, but again, at the end of the day, they occur randomly. So how do you account for that? And then lastly, we have a scenario where we have a repeatable failure mode that occurs generally the same way every single time. And we have different approaches for handling each of these scenarios. So on one hand, like for scenario 1, where you don't know what to expect, this is where a technique like clustering and unsupervised learning becomes really valuable, right? You're not necessarily looking for a specific pattern, but you're looking for new patterns. You want to understand that pattern, how it develops, and what it looks like in context with all the other normal patterns for that machine. So with an unsupervised approach and a clustering approach, you can actually develop a good understanding of how that asset behaves and when it's in an anomalous state. And again, this is where there's a strong handshake with that SME to make sure that makes sense. And had a question over there that I just was a question, yeah.
So, the previous slide you said, AI cannot fix the infrastructure problems as regards to data, but I thought there was a follow-up slide. That's why I thought you were going to transition into another thing. So who do you place the responsibility on for this? So if you are using your tools, you're saying, your data is not consistent or whatever.
Sure.
Are you going to help us with that, or I mean,
Sure. So SparkCognition can help provide you guidance and the right introductions with partners that work on the data side. Again, we're on the receiving end of data, so we will work, if a customer is in stage 1 of their digital transformation, we work with our partner National Instruments to help instrument the sensors. And then we have we have OSI Soft as a partner as well. So that would be the solution for helping to orchestrate the data problem. But it's also up to the business itself, right? Do you have the business structure? Do you have someone a dedicated resource to actually manage the data and is mapped to the vision that you have for the machine learning project? Because if those aren't in sync, it's really hard to actually deliver value from a machine learning project. Does that answer your question?
so you provide that as a service to help the customers?
We can provide guidance and introductions to the right people for that. Okay, so kind of moving through this again. So scenario 2 is where it might be best to actually use data from when that asset was in a normal state to build a model of what normal looks like, and then compare all future behavior against that benchmark of normal. And this is used for complicated assets, it's used for simple assets. This is a really powerful approach that is somewhat in the middle. And again, if we know a little bit more about that failure, we can train on, we have historical data from that asset, we can build a really sophisticated normal behavior model. And then lastly, if we know how the failure mode develops and we know what that looks like and we have a ton of historical data showing that we know how that happens, we can build a supervised model that if we match that pattern, we can raise an alarm to actually perform maintenance or fix the problem. Now, as we get into the explainable AI approach, this is where we're providing insights in a couple different ways, right? We can compare clusters, we can compare the different patterns of behavior, we can highlight the top contributors or what's most correlated to that prediction. We can provide a risk assessment, and then at the end of the day, the SME can actually label that failure and train the model so that it knows to expect that failure mode at a future time. And this is all part of that retraining of the model, part of that continuous learning piece that is what I get really excited about machine learning. This is learning from new data over time. How can we start to codify the SME knowledge into that model, into those algorithms, and learn and support it with new data?
So Gabe, with the clustering piece, do you take multiple oil and gas customers who have your package in place and kind of leveraging their data to refine the overall algorithms for your oil and gas predictive maintenance package? So if you got 5 or 6 customers that are all running your package for the past year, you pull all that data and insight to then refine, I guess, your solution that you sell into that market. Is that the clustering approach, basically?
Clustering is a data science approach used to identify the different patterns in data. Now, we do exactly what you're talking about. So every project that we work on, we're bringing the learnings, we're bringing the IP that's developed, we're bringing that back into all future projects. But clustering specifically is a data science approach for solving an unknown problem, or finding an unknown pattern.
But I think with IoT, it's going to be important to do what you say, where you have a certain type of sensor or a certain motor, and you build models around that motor with customer A, and now you're an expert on that motor that can sell into customer B, C, D, E, Z.
Yes, the domain expertise that we collect in-house comes from working very closely with actual data scientists and SMEs at our customer sites. So you're absolutely right. With each project, our team gets better at understanding what works, what doesn't work, and what the different failure modes mean, and it's part of the ongoing R&D process.
Are you then training that into a meta neural network or a meta AI to learn what the SMEs know?
That's complicated. We're not there yet.
I didn't think so, but I thought I'd ask.
Yeah. We're not there yet. Yeah, any AI company that gives you a yes, be cautious with that. That's some of the groundbreaking research that will be important for scale, right? How can we generalize, and that's transfer learning. How do we generalize the behavior of a valve against a completely different set of valves, bigger scale? How do we draw those insights and correlations so that we can deploy a model built on valve A without having any data from valve B?
Or how do you take the task of analyzing model A and apply it, to model B?
That's your transfer learning from earlier, right?
Yeah.
Well, there's transfer of an existing model from one type of product to another. I'm asking about one level up, transfer of, training an AI on the process of analyzing a model.
Yeah, we're not quite there yet.
It's called an IDE.
Well, right, but it requires a human is my point.
So moving into what's real, right? I'm going to call out two industries that are undergoing a lot of change right now, and the fit for machine learning within these particular industries. So on one hand, oil and gas, their new reality is that they're having to deal with a lot of fluctuations in oil prices, right? And this is changing how they operate their rigs. This is changing how they resource things. This is changing how they respond to that volatility, because in the past it's either been oil's been good or bad. Now there's all this movement in between. On the other hand, we have power generation, which is having to deal with the problem of new resources on the grid. So think about the emergence of renewables. The reality is that traditional thermal power generation, is having to operate their assets in a different way as well. Something that they haven't trained models for, something that they don't have experience doing. And as a result, those assets are performing differently, and those assets are potentially failing differently than they've ever seen. And both of those industries are faced with the additional challenge of just their own SMEs, their own experts are leaving the field due to retirement, and there's this huge knowledge gap. Now, one of the ways to fix both of those problems is through better maintenance practices and technology. And this is one area that's pretty well established, but is a really good fit for machine learning. We have an example of a customer that we're working with on the oil and gas, so thank you for the oil and gas plug, Tim. But we were working with a customer, one of the super majors who has deployments in the Gulf of Mexico, and they came to the problem of, typically their platforms are experiencing 5 to 10 production impacting events per year, right? So 5 to 10 times their production goes down to 0, and it takes them about 12 hours to actually fix it, scramble the resources, get the part, whatever has to happen. Now, based at oil at about $65 a barrel, every time that happens, that is a $6 million hit to their production. So you escalate that, so 5 to 10 events, that's $30 to $60 million every single year that is on the table because they have to scramble and react. They can't anticipate and plan for that failure. And then you multiply that across the fleet, and this gets to be a very large number very quickly. So they came to us with that fundamental problem of how do we get better at understanding and predicting when these unexpected outages are going to occur. So we got data, and I'll walk through a little bit more about that project in a second. But the highlight of that is we actually caught 75% of their events, right? And instead of their normal 3 to 4 day lead time, we gave them 9 days on average of lead time, which is huge. We gave them an extra week to be able to figure out and plan and make sure that they can do the maintenance so that unexpected outage doesn't happen. Now, we kind of zeroed in, and after doing some post-analysis, like for the initial pilot, this is around, they wanted us to look at some of their main problem assets, right? So there were 3 that we looked at in particular. There was 2 export compressors that were equipped differently, instrumented with different sensors, and they're at different stages of their life cycle. And then we had a glycol system as well that typically these 3 assets cause about 80% of their unexpected events. So we zeroed in on those and built the models. And the model building piece started by reducing all of the data that they had to only the most important data. This is a data science term called dimensionality reduction, but we're actually trying to filter out all the noise in their data to understand, okay, what were the actual drivers, the most important drivers of that outage. So by doing this, we were able to build a model. We used clustering because these were unexpected failures. We didn't quite know how they developed. We used a clustering approach to build the initial model. And we were able to also give them some insights into what the different operating states were of these particular systems. And then we were able to provide additional insights like, okay, how long were these assets in an anomalous state? Were there any other things that they needed to look at? Now, we did get a few lessons learned here. So on one hand, this is an exercise in scale, right? So we went through the pilot. They asked us to deploy on their first platform to kind of extend that pilot. And we built 40 individual subsystem level models in 4 months and deployed on platform 1. Platform 2, and they were like, all right, great. Platform number 2, we did the same level of work in 2 months. So this is your point about bringing the insights and all the learnings from that first platform to the second platform by using repeatable technology, repeatable approaches, and our own internal products and platforms to actually drive scale, because this is a hard problem. And what I do want to call out is that each of these assets has its own model built using its own specific data. And we found that this is very important because if you have a generalized model, it's not tuned to that asset, and you're going to get a much different level of performance than one that's actually trained on its own data. Yeah.
So after a repair, because they change out some parts, do you then have to retrain?
Yeah, so there's a retraining process.
Okay.
And again, this is ingesting a little bit more data, retraining the model, giving the model some additional parameters, and we're working on automating that process as we speak so that with the vision of it being as simple as a couple clicks, the SME or the analyst can actually retrain the model and deploy it with minimal effort. Now the goal is to take this all the way from 4 months down to 2 weeks, and we're really confident that we can hit that benchmark.
So you're trying to do proactive maintenance instead of preventative maintenance? Does that make sense?
I think, yes. Essentially, we're trying to give enough insight and warning ahead of time for maintenance to either be, for the right fix to be either scheduled or integrated with maintenance that's already been scheduled, or order parts if they think something is going to break. We're trying to give additional insights so that the actual maintenance process can be improved.
By monitoring parameters, you're monitoring certain parameters, and because it's in this area, then you say, we need to go in there and do some proactive maintenance.
Yeah, so there's people that are performing maintenance by going around and actually listening to how a pump, like they put their ear up on the pump, and that's how they can tell whether the pump's in good shape or not.
Okay.
We're trying to use data to extend, but you don't have a human there, you can't predict when that pump is going to fail. But by using data, we can give a little bit bigger of a window into when that pump is going to fail and how it might fail.
Earlier you said that there was a 3-day lead time and you guys extended that to 9 days. Can you explain that a little bit more detail? They were actually identifying things, but they just didn't do it early enough to get parts on order? Or were you guys actually finding things they didn't find?
Yeah, so there's kind of two pieces of that. In one case, there's unexpected stuff where they can't plan for them, it goes down, and there's no lead time. There's also some cases where they have some basic monitoring where there is where they've got, in addition to those 5 to 10 events, they have other events that they typically have 3 to 4 days of lead time. And so they came to us with that benchmark. They were like, all right, typically for most of the events that we can catch and fix, we've got 3 to 4 days of lead time. Can you beat that? That was how they came to us.
But that wasn't all of them. You guys caught stuff they didn't catch at all.
Yeah, exactly. And it's a good point. So the value of this scale and the value that we're able to, they're actually able to get value out of all their digital investments are meaning two things. Well, meaning one important thing for them, or two important things for them. First, they're able to prevent more failures and increase their top and bottom line. And second, they're able to reorganize their resources, pull some of their monitoring resources, maintenance resources from offshore, onshore, and consolidate and build remote monitoring center to actually handle this at scale now that they know that they can get insights across their entire fleet. So they're consolidating resources and making it easier to actually monitor and manage these assets. Now, based on that success, we were able to win another contract with Aker BP with a similar use case within 6 months. So again, this technology, my point here is that this technology is real, it's useful. We have customers that are using this to drive a lot of operational efficiency and production maximization. We also learned a few things, right? So part of this was, okay, we learned how to score a model, how to figure out when that model is going to be a high quality model and when it's not. So we built some internal IP to better validate earlier on in the process if we were actually going to deploy a good model. And then handshake with the SME and the data scientist team on the customer site to actually make sure that makes sense. We're also able to point out some really interesting things in the data that they weren't expecting. Right? This customer got some additional insights around when there was unexpected human activity on the offshore platform. Some seasonality issues as well that they didn't previously have insights to. So by being able to extract that information from the data, even though we were trying to approximate physics, we also were able to figure out some of the intangible stuff that they weren't expecting. So this is, again, helping them refine their process, helping them figure out how to better optimize and maximize production.
When Joe was on shift, they all broke.
Yeah, exactly. Well, there's an interesting case where apparently they send all their new folks out there right around Christmas, like all the seasoned guys come on shore. They send all the rookies out there, and you see more operational problems because there's that difference in subject matter competency. So we didn't know what that meant, but we told them that, hey, this is something that we identified. Can you guys help us explain it? And that's what ended up happening.
Hey,
Yeah.
on the modeling, are you guys finding that the accuracy of the model is more dependent on the industry or the company versus the device itself? So, for example, if BP and Aker buy the same pump, do you expect the model to be more dependent on the pump, or how those two different companies use that pump?
That's a great question because it depends on location of that pump, right? Is one in a cold condition, one in a hotter condition? How that pump is used, is run 24/7, is it run periodically? All of those are different. And so you could have even two assets running right next to each other that are operating very differently and have to have their own individual model. So that's the power of being able to develop an individual asset-centric model at scale, right here. Did you have
I was just saying the quality of the electricity going into the pump too.
Yeah.
Right? If you got a bad brownout situation, you don't know that.
Yeah, there's tons of factors and that's why it's specific to train that model on pump-specific data.
Gabe, how do you avoid overfitting your model, when you're trying to create it? You don't want to make it perfect, right?
Yeah.
So how do you make sure you don't go too far to making it perfect so it's not effective once it gets deployed?
Yeah, no, great question. Machine learning is a lot of balance, right? It's balancing the right amount of data. It's balancing the data science techniques and the science with the actual subject matter experts. So the fix for that is that handshake between the SME and the developers of the actual model, right? We can approximate stuff, but it still has to make sense, right? And we have to account for a little bit of variation, a little bit of flexibility, but the accuracy of the model is going to depend on all of that process working together.
It actually comes down to how much of data you have as well, because it is very easy to end up with a model that overfits your training data,
Right.
and then it becomes too specific. So the idea is to get a wide representation, and the division between the training set and the test set also matters.
So how do you guys determine when you need new data? Like if something's not instrumented, maybe I want a temperature sensor here or a vibration sensor here, how do they go to that? Do they have to rely on experts, or do they just overreach and instrument everything, figure out what works, and then remove stuff?
So there's a couple different ways to that. So, I mentioned the first step of this is trying to figure out what data matters to the actual prediction. So if we have experience with the pump, we can typically understand, okay, what is the baseline data source, the baseline of data sources that we need to actually make it work and usable. So, sorry, I lost my train of thought here.
I'm sure you start with what you have, right?
Yeah.
But then at some point, some expert or some data scientist looks and says, I probably need something more. You know, is it just a onesie twosie, or do you prefer to go and over instrument during the initial phase and then pull back and refine it to something to the bare minimum?
Yeah, usually we're working with from over instrumentation and filtering that down. In some cases, you know, we'll do a data assessment early on and quickly be able to visualize and say, hey, is this data even usable? And then make some recommendations on what to do to fix that data quality to bring it up to the point where we can actually build a model for it.
Well, I presume if you get a lot of new events, new failures, that would indicate you might need new instrumentation.
Exactly. So one of our major sets of customers are actually the OEMs themselves, right? They have the access. They're trying to figure out, okay, how do we maximize the sensor package on this pump, for instance, or this reciprocating compressor? How do we make sure that we're getting the right amount of data without spending money unnecessarily?
Gabe, I'm sorry.
Yeah.
On the last slide, you had a footnote that caught my attention related to these questions. And on the lower right says identify when the model starts to drift. I don't know if that happens all the time, but does that mean this is an ongoing process, or just deliver and kind of stop?
It's very much an ongoing process, right? So once something is actually in deployment, we're hooking and connecting to live data streams. Now, so we're getting the initial model is running against brand new data that's coming in. Sometimes what starts to happen is, you know, as maybe we have a really hot summer, maybe we have other factors that cause that model to become a little less accurate. We can start to flag and understand, okay, what is this model right for retraining? Like, do we need to actually take another look? So it is very much an ongoing process, right? This isn't a one size, deploy the model, go. In many cases, it's an iterative process. So part of the research is, okay, how do we get really good at making that retraining process with the new data as easy as possible? Because it's a hard problem, frankly. So I won't spend a whole lot of this time on this slide because I've got about 10 more minutes. But essentially, the similar story for what we've done in oil and gas with energy and utilities, right? A power plant is a collection of really complicated critical assets that are equipped with IoT sensors. There's a lot of subject matter expertise being put at these problems because if a turbine fails, one, it can be a $200 million asset, and it can cause $13 million in lost opportunity over a month, right? So the numbers are big here. We're working on a first-of-kind deployment for an entire power plant. Typically, these customers are a little bit more cost-conscious, and they're looking for an individual asset model. They want a model of their combustion turbine, or they want a model of a smaller combustion turbine or a generator. This is the first time that we actually equipped an entire power plant, or nine models across 2 combustion turbines, a steam turbine, the generators that go with them, the HRSGs, the condenser system. We made models for all of that and are in the process of deploying that as we speak. Now, the math hasn't been done to calculate that ROI, but the expectations, and by triangulating with some of what the analysts are recommending, we think we can get a 20 to 30% productivity boost for this power plant. Which is really important because, again, the assets used at power plants are being used differently than they ever have been before. And with renewables coming online, a lot of these power plants are starting to sunset, right? And the goal now is to minimize the actual costs as that plant goes into life. So I think one of the questions here is really like scale, right? I've talked about scale a lot today, and this is a hard problem to solve. On one hand, we still have data science teams that are building these really complicated models, but how do we support them? How do we actually enable that to happen at scale, right? Because data scientists have a very specialized area of expertise. It still takes time to build a high-performing model, and they may not always have the right tools at their fingertips to build this. The good news is a lot of this can be automated, right? So if we look at the entire process for building a model, we start with a data set. We have to do some preparation, some cleaning of the data, make sure that the data makes sense, that there's not too much missing data. We then do some feature engineering and extract, okay, what is important to the output of this model, and then we build the model. That can take a lot of time. And it happens over and over, right? You build that initial model, and then you have to iterate on that model until you come up with a result that meets the business criteria. Good news is that we've actually figured out a way to actually automate a lot of this process. And essentially what we're doing is we're taking data, and then we're using machine learning to help build that machine learning model. It's through a process called neuroevolution, where essentially we'll take data that comes in a spreadsheet, we'll spawn off an initial model, and that model, depending on the parameters that you give it for training, whether you train it for 10 minutes, whether you train it for 2 days, you specify certain parameters in the problem that you're trying to solve within that rectangular data set. And behind the scenes, we're automating the generation of that first model, and that model is building additional generations within the training parameter time set. So in that process, the model is specifying what approaches work. So if you're familiar with data science like XGBoost or random forest algorithms, starting there and then specifying, okay, how many layers in my neural network do I need? We're actually building that behind the scenes to come up with a unique model that solves that problem with very high degree of accuracy. So this is one of the ways that we're able to deploy at scale, right? We can rapidly prototype, we can rapidly generate these iterative models to move a little bit quicker. And the good news is that for certain applications, this technology is available for the citizen data scientists, for the data scientists, for analysts. It's usable to a much broader audience than just data scientists. And these are some of the use cases where this can be deployed. Again, if we've got data and we have a decent understanding of the problem that we're trying to solve, we can use AutoML tools like Darwin to model asset behavior kind of on an ad hoc basis. Look at transactional data to predict customer churn, which customers are going to be with us long term, which customers are high risk of leaving. We can optimize when we need resources for a certain work over, or how do we staff our call center to make sure that we can handle a higher expected demand of calls. In the financial domain, right, we can use both traditional sources and non-traditional customer data to make predictions on stock market. We can determine credit risk based on a customer's profile and all their activity. And then we're even using Darwin in cybersecurity, where we actually are building predictive machine learning models to detect malware without having to use any references to signatures or heuristics or rules. So this is what I find really exciting, really exciting about the future of machine learning, right? This is becoming democratized to a point where you don't need the same level of data science background to be able to use powerful tools to solve key problems.
On your center thing on financial services, how is that different than what Lemonade is already doing with their online property casualty insurance?
I'm not familiar with that.
Lemonade is a startup. They wrote about 60-70 million in premium last year. It's entirely online, targeting to millennials. Forbes recently did a story on it. They had a guy put on a blonde wig, necklace, and everything like that to fraud him for like a $600 claim. By the second claim, he had sent in a different name, email, and address with their algorithms and caught him. Aren't they already doing what you're saying they're doing? I know that seems to be the only one.
There's likely some machine learning in their back end. I wouldn't doubt that others are doing this, but it could be that they've got their own data science team handling this. I don't know the details, but we can talk afterward on So just a few more slides before we kind of open up for questions and wrap off the books. But putting this all together, again, we have two platforms. We have DeepNLP and Darwin, which is enabling us to handle both unstructured data and structured data. On top of that, we deliver value to customers through solutions, through vertical-specific solutions like SparkPredict, which is our predictive maintenance solution. And we can also use this technology, a combination of these technologies, to power some really cool stuff like SkyGrid. This is our joint venture with Boeing to actually plan and develop the autonomous air traffic control systems of the future. So it's some pretty cool stuff. Again, yeah.
I was waiting for it.
So over the last couple of years, right, we've gone from a point where this technology was really, really new. It was a lot of innovation, a lot of groundbreaking stuff, a lot of innovation in the model building piece in particular. 2018, and this is where we were talking with a lot of innovation teams. These guys are looking for some experiments. In 2018, the technology became incubated, and we started making that transition the industry started making that transition from individual projects to more scale. And now in 2019, we're implementing. So the decision-making process has moved from the innovation teams to the business units because the operational technology is real and it's providing value. And there's a risk that if customers don't have a strategy in mind for AI or machine learning, they don't know how to put it in context, but they have data, they have problems, they're very much a risk of being left behind. So something that we try to help coach and help customers understand that this technology is moving very quickly, and if you don't have a plan for it, it could become a competitive disadvantage. So 3 things to think about if you're thinking about a good AI project. Do you have data? I hope that came across in the presentation. Do you have enough data to build a good model? And is your problem complex enough, right? A lot of people are trying to use machine learning for problems that don't need machine learning. And they're spending time and resources on stuff that could be solved with other technologies that we have today. So pick the right problem. And 3, it could be fun to spin up an AI project or a machine learning project, but how is that actually going to translate to your business impact? Have you had that conversation? Can you trace back? Can you start with the business problem and work your way backwards rather than working from AI and trying to use it to solve an unknown or an unspecified business problem? So only one last slide here. If you guys are interested in learning more, we do have a Thought Leadership Conference. This is our 3rd year running in Austin, Texas. It's called Time Machine, and it's November 13 to 14. And this is where we bring a lot of the thought leadership around AI and emerging technologies all under one roof. So if you're interested in learning more, if you want to engage with some of our customers and engage and learn from people that are doing this every single day, come out to Time Machine. It's a heck of a fun experience, and you'll learn a lot. So yeah, that's my time. Thank you guys all for the questions. I'd be happy to. I'll probably stick around for another 45 minutes to an hour, and happy to engage. But thank you guys so much.
All right, let's give it a